Yeah, hi. Talk about, again, continue with the two sample inferences and or two populations. And in this today, we're going to talk about population proportions. When our populations are binomial populations. So we have two binomial populations, and the parameter of a binomial. Remember, the parameter for a binomial distribution is the P, which is the probability of success. So in this case, we have two, and so the parameters are P1 and P2, probability of success or proportion of success in the first population, proportion of success in the second population. So we're going to pick two samples. Sample 1, we pick sample of size N1. We have X1 successes, so the proportion of successes in the sample is X1 over N1, and that's our estimate for P1. Same thing for the second sample, and that's our estimate for P2. So the estimate for P1 minus P2 is going to be P1 hat minus P2 hat. So remember, P1 minus P2 is an unknown parameter, and its estimate is what we get from the sample, P1 hat minus P2 hat. We also need to specify alpha, which is our significance level. The mean for this parameter, for this estimator, mean of P1 hat minus P2 turns out to be P1 minus P2. This is again a good property which indicates we have an unbiased point estimator, but by itself is not sufficient to give us good estimation because we need the margin of error, because if the margin of error is large, this is not going to be that much useful. So we also need the for that we need the standard error of the point estimator, 0.1 hat minus P2 hat, and that turns out to be P1 Q1 over N1, P2 Q2 over N2, and the hat indicates these are estimators. Remember, Q1 is 1 minus P1, so if P1 is 0.6, this would be 0.4, and Q2 hat is 1 minus P2. So now for the confidence interval, the formula would be same overall formula. We specialize it for this case, the point estimate for P1 minus P2, which is P1 hat minus P2 hat, plus or minus the margin of error, which in this case, since we have large samples, would be Z alpha over 2, and then we multiply that by the standard error, which is this quantity here. And for this formula to be valid, we needed large samples, which means N1 for binomial population. The test for large samples means N1 P1 larger than 5, N1 Q1 larger than 5, N2 P2, and N2 Q2 all larger than 5. And we need the samples to be random and independent. Okay. So if I want to control the margin of error, sometimes I want to control that margin of error and pick a sample that guarantees like 3% or 4% or 5% margin of error in this case. So in this case, that would be my formula, which is N equal Z alpha over 2 squared times P1 Q1 plus P2 Q2, and we use the estimates over E squared. Remember, before we had just one of these when we had single sample, now we have two. So if the parameters are not known, we got this product would be maximized if P and Q are equal, 0.5, 0.5 each, since we talk about percentages, and the same thing here. So if the parameters are not known, we use just 0.5, 0.5, 0.5, 0.5. Okay, so that gives me 0.25 plus 0.25, and so this the whole quantity here would be half. So and that gives me the formula for when the parameters are not, we don't have unknown estimate, we don't have good estimators for the parameters. For testing hypothesis, same idea. The parameter we want to test is P1 minus P2, and in this case we want to know whether P1 minus P2 is 0 greater than 0 or less than 0, which means the two populations have equal parameters, one is larger or one is smaller. So for this, we need the sample size N1, X1 and their ratio, which means that gives us the estimate for P1. Same thing from sample 2. This is the unknown parameter. Our significance level would be 5% if it's not given. That's the default value. And my point estimator for the parameter is P1 hat minus P2 hat. One thing we're going to need now is the common estimate. So if I were to pool my two samples together, what would be the estimate if I assume P1 and P2 are equal? What would be the common estimate for that common parameter? And that would be the successes in both samples plus the sample sizes in both sizes. So we call that P hat, and Q hat would be 1 minus P hat. Tell you in a minute why we need that. So here is my test. Remember, we always assume H0, the null hypothesis, is equal to 0, P1 minus P2 equal to 0. So because of this, we assume P1 hat minus P2 equal to 0, and we try to prove one of these hypotheses, which is like a proof by contradiction. So assuming this means we assume P1 and P2 equal to 0, and that's why we need their common estimate. Okay, so it makes our test more powerful. So now we have an upper tail test, a lower tail test, or a two-tail test, which is not equal to. And the test statistic would be the point estimator. It's the same for any one of these three tests. Point estimator minus the right-hand side, which is 0 in this case. And then I want the standard divided by the standard error. But since I use my common estimator, so my standard error here would be, if we go back here, where is it? It's this one here, P1 hat, Q1 hat, P2 hat, Q hat. So if I have a common estimator, I'll use PQ here, so I can pull that outside. And that's what gives me this value here. Anyway, so if you remember, this is P hat, Q hat, 1 over N1 plus 1 over N2, and I want the square root of that. And since I will use a large sample, my rejection region is going to be reject if I have the upper tail reject H0 if Z is larger than Z alpha. So this is upper tail, and the greater than indicates upper tail, less than indicates lower tail, so Z would be less than negative Z alpha. And two tail means either larger or smaller, so that but alpha is split into 2, so I reject if Z is larger than Z alpha over 2 or less than negative Z alpha over 2. So same as before, and I'll show you the graph for this example here. So, and in this case, we need the assumption that our samples are large, they are random and independent. So if we do these graphs here, let's go and do the graphs for the, so in this case, I want to have my first test is here, HA is P1 minus P2 is greater than 0. And in this case, I would have a graph that would look like this. Because my center limit theorem tells me this is going to be a Z, and this is my Z alpha. So alpha is this area here, and this is my rejection region, and this is here my non-rejection region. And so my Z, the test statistic, if it's up there, I would reject. If it's down here, I would not reject. Okay. And the same thing for if HA is P1 minus P2 less than 0, then I would have another graph. It would be similar, except I would have negative Z alpha here, and this would be my alpha. This would be my rejection region down here, and this would be my non-rejection region. And if I have P1 minus P2 not equal to 0, then my graph is going to be like this. Still a Z, and I'm going to have a Z now alpha over 2, and here I'm going to have negative Z alpha over 2, and so this would be my rejection region, and this would be my non-rejection region, because this would be my alpha over 2, and this would be my alpha over 2. Okay, so if I go back to my example, suppose now I want to test the hypothesis that P1 minus P2 is less than 0. That is, the first population has a smaller probability of success than the second one. And I already know that Z is negative 1.91. So how would I solve that? So I will set up this problem. Now P1 minus P2 equals 0. The alternative P1 minus P2 is less than 0. And since this is a lower tail test and I don't have any alpha given, I use alpha 5%. And the corresponding critical value would be negative Z alpha, which is negative 1.645. You can get that from the table. And so my rejection region would be reject H0 if Z is less than negative 1.645. The graph would be, so which graph would I be working with here? And so it's going to be this test here. So I'm working with this one here because it's a lower tail test. My Z alpha is negative, negative 1.645, which is this value here. And my Z is down here because it's negative 1.91. So this is less than this, so it falls in the rejection region on this side, and therefore our decision would be to reject H0. If it was up there, we would say do not reject H0. Okay, so now let's go back to complete this. So now we reject H0, so we reject H0, and the conclusion would be at 5% significance level there is sufficient statistical evidence to conclude that P1 minus P2 is less than 0. Okay. I want to go over small inferences about the difference between two means. Remember, in this case we cannot deal with proportions. So in this, everything is the same as we had before. Parameter of interest is mu1 minus mu2. Our sample data is n1, x bar 1, s1, n2, x bar 2, s2, d0 is called target value, and we are given alpha. As before, the point estimator is x bar 1 minus x bar 2. The mean of the estimator is mu1 minus mu2, which indicates that we have an unbiased estimator. Our assumptions here, our populations have to be normal, unlike the large sample case. And the variances of the populations are not known. So if they were known, we still use the normal population. Small samples, we have n1 less than 30, n2 less than 30, basically, or just basically we are estimating the parameters. Samples are randomly selected, they are independent, and we can assume there are two methods, one method for when the variances are equal and another method when the variances are not equal. So we only want going to cover the case when the variances are equal with a common variance. So the variance is equal. So in this case, because the variances are equal, we're going to need one estimate for the common variance. We call it the pooled estimator for the common variance sigma. And the way we obtain that is we take the sample variance S1 square. Remember how you look inside. And the sample variance S2 square. We multiply the first one by N1 minus 1, the second one by N2 minus 1. We add them up. We divide by N1 plus N2 minus 2. This happens to be our degrees of freedom for this case. And that gives me the pooled estimate for the sample variance. If I take the square root, I get the one for the standard deviation. And so the estimated standard error, then that would be sigma, which is I can estimate it by S times the square root of 1 over N1 plus 1 over N2. And the reason for why we get this is because if you remember, the variance for x bar 1 minus x bar 2 is given by this formula, but now my variances are equal, so I replace them by the common value, and that's sigma square. I can pull it outside. Okay, so that gives me this value here. And you can see immediately from this that x bar 1 minus x bar 2, I can get my confidence interval now plus or minus the point estimator plus instead of z, I get the t values, t alpha over 2, and this is the degrees of freedom here, tells me, and that's my standard error S square root of 1 over N1 plus 1 over N2. So that's the formula for the confidence interval. For testing hypothesis, same thing. Mu1 minus mu2 equal D0. This is my upper tail test, my lower tail test, my two tail test. What's really difference here is two things. First, it should be a T, not a Z here. And the other thing is the denominator. The standard error is slightly different because we are using the common estimate. So it's S, which is the common value obtained from here, times the square root of 1 over N1 plus 1 over N2. And our critical value in the first is T alpha. Remember, the degrees of freedom will always be the same, N1 plus N2 minus 2. And it's negative T alpha if it's a lower tail test for the second one, and it's T greater than T alpha over 2 or T less than negative T alpha over 2. And we should be able to compute these from the T table. We learned this before. So here is a quick example on this. If I have now small samples, I know they come from a normal population, but I don't know the variances. I estimate the variances, and in this case I have N1 7, N2 8. I have alpha, and I already used all the information to calculate T, which is 2.2. So just to save us our time. So in this case, if I want to test that the two population means are unequal, I use the formula, I substitute in it, and I should get 2.2. But if I go to, since this is a two-tail test, my alpha is 5%, because my critical value would be T.025, and the degrees of freedom would be 7 plus 8 minus 2, 13. So if I go into the T table, that should give me 2.160. So remember, my rejection region would be same at either greater than 2.16 or T should be less than negative 2.16. And if I were to graph this, it's going to be exactly the same as this graph. Since I have two tails, the only difference is the z would be replaced by a t, and this would be a little bit flatter curve, and I need the degrees of freedom for that t to find out those values. Okay, so that's basically what would be changed. And since we know how to compute t values now, I'm gonna leave that. So now we compare this t, which is 2.2, with the critical value, which happens to be greater than this value in the upper tail. So we reject H0, and our conclusion would be at 5% significance level, there is sufficient statistical evidence to include that the weight loss in the two-tail programs are different. So next video will be on the small sample inference when we have paired samples. Okay, thank you.